All right, so looking at do now, this should seem relatively familiar. It looks similar to a homework problem that we had. So looking at it, we're looking at our two events are whatever happens on the two consecutive nights. So let's just call this night 1 and night 2. And these can be our outcomes. So outcomes, sorry it's so sloppy. All right, outcomes. So what can happen in night 1? Obviously, well, each of the individuals could win. So that would be Alice, Bill, Chester, or David. And in night 2, coming off of each of these is our tree branches, Alice, Bill, Chester, or David. And so we can see that there's going to be 16 outcomes here using our tree diagram, and it helps us in an organized fashion kind of figure out what all of those outcomes are. And so when we make our list of outcomes, we just follow our tree diagram. Okay, so our first diagram goes from A to A. So that first outcome is AA, and then AB, then AC, AD. Coming from our B tree diagram, that's BA, BB, BC, and BD. CA, CB, CD, and coming from the last one over here is DA, DB, and DC, and DD. So we have our 16 total outcomes. It says, what is the probability that Bill will win both nights? Is the probability that Bill will win both nights the same as Alice wins in the first night and Chester wins in the second night? So if we're looking at this, the probability that Bill wins in both nights is here. That's the BB, that's the Bill wins both nights, and then Alice first, Chester second. So that's very clearly A then C, not C then A. And so we see that there's one answer here. So are the probabilities the same? And our answer is if all probabilities are equally likely, then the probabilities are both 1 out of 16, because only 1 out of the 16 criteria meets. So we learned yesterday that there were some times, and we don't give any information about this, because what we see here is we actually don't have to go through and do the calculations, because we know that all of the outcomes for each individual night are equivalent. They're all equal to 0.25. So that helps us out with that. All right, so let's flip on over and look at our aim for today. Today's aim, Kipsters will be able to solve compound probabilities with tree diagrams. Tree diagrams. So what we've seen before is we've seen tree diagrams where there were two individual events. Today we're going to push our knowledge just a little bit further to see what it would look like if there were more than two tree diagrams. So as we look over this, our previous example from yesterday, we were talking about a family that decided to play a game each night, and they rolled a die to figure out which game they were going to play, whether it was a board game or a card game. And we made the tree diagram for 2 consecutive nights to look like this. Monday they could play a board game or they could play a card game. Tuesday they could play a board game, they could play a card game. And so we got these 4 individual outcomes. So how would the diagram change if we were interested in mapping the possible outcomes over 3 consecutive nights? So now we add another branch after each outcome. So this is really like, once we get here, BB, this was like our BB outcome. From our BB outcome, the next night we can either get a BC or a B or a C. So we end up with following this pattern, following the trail, B, B, B. And then this outcome, B, B, C. Following all the outcomes, B, C, B, B, C, C. Okay, so each of these end paths is going to have its own specific coding for the outcome. And so what we can see here is that there's a total of 8 outcomes. And sorry, this got cut off. C and C. And so this last one down here is C, C, C. We can see that, and what that kind of tells us in another way we can think about this, there's 2 possible events, 2 possible outcomes, 3 different events, 2 times 2 times 2. That's how we should know that there are 8. So coming over here, if BBB represents 3 straight nights of board games, what does CBB represent? Go ahead and answer that question. Actually, answer questions 1 through 3. So if you haven't paused the video and you haven't answered those 3 questions, please answer those questions 1 through 3 with your partner. All right, so CBB would represent a card game, then a board game, then a board game. So this is, in some form or fashion, night 1, cards, night 2, board game, and night 3, board game. The next question asks us to list all of the outcomes where exactly 2 board games were played over the 3 days. So we're looking for all of the ones that have board games being played twice. So as we come down here, this one has board games 3 times. This one is 2 board games, 2 board games, 1 board game, 2 board games, 1 board game, 1 board game, no board game. So it looks like we have 3. So we're going to list all of those outcomes. It's BBC, B, B, C, B, C, B, and C, B, B. All right, those are our 3 outcomes. There are 3 of them. So how many outcomes were there? There were 3. And finally, there are 8 possible outcomes representing the 3 nights. Are the 8 outcomes equally likely representing the 3 nights? Are the 8 outcomes representing the 3 nights equally likely? Why or why not? So at this point, based on the information we know, there's nothing to tell us that the outcomes are going to be unequally likely. So remember, we learned yesterday that as long as each individual outcome was equally likely, then all of the final outcomes were going to be equally likely. So far, based on what we know, they would be equally likely. However, if we remember from yesterday, when they chose the board game, they weren't all equally likely. So for now, we could say, as long as B and C are equally likely, the final outcomes are equally likely. All right, so that is the one thing that we've learned. As long as all outcomes in each individual event are equally likely, then each outcome and final will be equally likely. So coming over here, in the example that we talked about, so we're going to move over to those last 3 questions actually are associated with this bottom part. In the example that we were given, each night's outcome is the result of a chance experiment, rolling a 4-sided die. Thus, there's a probability associated with each night's outcome. So now this is where we get into determining whether the 2 events are actually equally likely or not. Now this goes back to what we talked about yesterday. We've learned that the family rolls a cube to decide, and if it lands on a 1, that's a board game. If it lands on if it lands on a 2, 3, or 4, that's a board game. It's a card game if it's 1. So we can see that these events are not going to be equally likely because the probability of a board game is going to be 3 out of 4, and the probability of a card game is going to be 1 out of 4. That's 0.25 and 0.75. So we use the tree diagram to find the probabilities. And what we learned about yesterday was we could follow the tree diagram and we could use it to multiply. So in each of these outcomes, we have the same thing. We have the combination of board game and card game being 0.75 and 0.25. But in order to do this work, we need to follow the probability. So this goes from 0.75 to 0.75 to 0.75. And the probability is just the multiplication of each individual probability along the path. So the probability of BBB would be 0.421875. So you guys are going to be working on your Chromebook, so you can use the calculator on your Chromebook here. Now if I'm following this path, BBC, I can see that it's 0.75, 0.75, 0.25. So to calculate this one, 0.75 times 0.75 times 0.25. And you guys can put that into the calculator to figure that out. So do me a favor, go ahead and calculate the rest of the probabilities for each of these final outcomes. So again, make sure that you've calculated them all, showing your work, what you multiplied along the way, and then come back and check in. All right, so we should have calculated all of our probabilities like this. Please go ahead and check your work, making sure that you did your multiplications correctly. Again, this is something you definitely want to use a calculator for, not necessarily moving forward. All right, so looking over here, it says the probabilities for 2 of the 8 outcomes were shown. Calculate the approximations. That's what you just did, taken care of. What is the probability that there will be exactly 2 nights of board games over the 3 nights? So that goes back to that other question. So remember, that's the combined probability of 3 of these outcomes. That's the combined probability of this outcome, and this outcome. So that's 0.140625. And actually, I see that there are 3 of them, and I would add them all together. 0.140625, 0.140625, and 0.140625. You also could have thought about that as multiplication, I guess, since they all happen to be exactly the same. But we go ahead and add that all together. And I'm going to get 0.421875. So what is the probability the family will play at least 1 night of cards? So go ahead and find all of the outcomes that have at least 1 night of cards. It says at least 1, so it could have 1 or more nights of cards. And you need to add all of those probabilities together. Go ahead and do that. Come check back in. All right, so I'm going to show you over here that you can see that I've circled and read all of the outcomes that have no cards. And this is where we can think about this is like, well, actually, this is all of them except for BBB. So really what I need to do is instead, I could add all of them up, which would be painstaking and long, but this is where that probability of, it's really just the probability of not BBB. So really this is 1 minus the probability of BBB. So I can think about this as being equal to 1 minus 0.4, I'm going to check in on that, 4.21875. And if I do that subtraction, we're going to get that the probability is 0.578125. So our probability, approximately 57%. So go ahead and flip on over and going ahead and looking at this problem, you should be drawing a tree diagram for this. This is, again, similar to a problem that you've done before. Go ahead and draw the tree diagram. Question number 2 asks you to add the probabilities into it. It tells you the probabilities are 0.5 and 0.5 to calculate each probability. Then answer the 2 questions. You guys should be able to do this all on your own and then come back and check in. So do this all, complete it, come back and check in. All right, so your tree diagram should look like this, and this should be your outcomes. We actually know all of the outcomes are going to be 0.5, so we can throw that into all of our probabilities and start following through again to find the probability of each outcome. This should move pretty quickly because you should recognize after the first one something specific. So go ahead and finish finding the probabilities and then check back in. So the probability for BBB that's going to be following that path is 0.5 times 0.5 times 0.5. And that's going to give me 0.06, nope, should give me 0.125. And as I start to follow these down, I see that actually they all have the same multiplication. So they're actually all going to be 0.125. As we walk over to answer the questions, we're going to try and figure out what these questions are asking us. The first one says the probability of having 3 girls in this situation. So the probability of having 3 girls, that's going to be just this one outcome. So the probability of 3 girls, the probability, and we're going to use our notation here so we can label our work. Probability of girl, girl, girl. You should have already answered this question, is 0.125. And it's asking, is this greater than or less than the probability of having exactly 2 girls in the 3 births? So when we look through this, having exactly 2 girls, that's actually 1, 2, 3 different outcomes. So the probability of 2 girls would be 0.125 plus 0.125 plus 0.125. So obviously that probability of 2 girls is going to be greater than the probability of having 3 girls. All right, what is the probability of the family of 3 children having at least 1 girl? Well, again, when we look through this, I'm going to circle the ones that have 1 girl, and I'm going to actually end up circling all of them except for 1. So this would be a good point to be like, okay, this is where I need to find the probability of not BBB. So taking the 100% probability and subtracting away the probability of BBB. So that's 1 minus the 0.125, and that's going to give me 0.875. All right, flip on over to your alone time and get your work done.